All the elements in the periodic table are made up of atoms, and atoms are made up of subatomic particles called protons, neutrons and electrons. Protons and neutrons are resided in the nucleus while electrons are moving around the nucleus. Positively charged protons and negatively charged electrons have electrostatic attraction. Neutrons are neutral. That means they do not have a charge. They are resided in the nucleus among protons to minimize the positively charged proton-proton repulsion. However, electrons do not have such support to minimize their negatively charged electron-electron repulsion. Therefore, electrons are moving around the nucleus on atomic orbitals or sub-energy levels with fixed energy to minimize the electron-electron repulsion. An electron configuration shows how electrons are distributed among the various atomic orbitals within main energy levels. Let's learn how to write the electron configurations for the first 10 elements and chemical concepts that are related to their electron arrangements. We use a standard notation to write an electron configuration. First we write the main energy level, then orbital type and number of electrons in that orbital as a superscript. An electron in hydrogen atom is moving on an s orbital which has a spherically symmetric shape. The first main energy level, also known as the n equal 1 level, can only contain one type of orbital, that is the s orbital. The s orbital can hold a maximum of 2 electrons. That is why the s block in the periodic table has 2 groups. The 2 electrons in helium atom occupy the 1s orbital with opposite spins according to the Pauli exclusion principle. An electron is significantly lighter than a proton. The mass of an electron is equal to 1 over 1836th the mass of a proton. For lithium, the first 2 electrons occupy the 1s orbital, which is the lowest energy level, and the third electron or the valence electron occupies the 2s orbital, which is in the second main energy level. Therefore, electron configuration of lithium is 1s2, 2s1. We can use noble gas electron configuration or condensed electron configuration to simplify the electron configurations for atoms with many electrons. For this method, we use preceding noble gas symbol in square brackets to denote co-electrons of the atom followed by valence electrons. For lithium, the preceding noble gas is helium. Therefore, we write helium in square brackets followed by its valence electrons as 2s1. Lithium is an s-block element since its valence electron occupies an s orbital. When we write the electron configurations, we can use either diagonal rule or periodic table. When we use the diagonal rule, we should write atomic orbitals of electrons in main energy levels as 1s in the first row, 2s, 2p in the second row, 3s, 3p, 3d in the third row, 4s, 4p, 4d, 4f in the fourth row and so on. However, when we fill the electrons to these atomic orbitals, we must follow the Aufbau principle, which says that electrons fill atomic orbitals in order of increasing energy. That means lower energy orbitals are filled before higher energy orbitals. The order of increasing energy of the atomic orbitals are not represented by either diagonal rule or periodic table. we need to know the order of increasing energy of these atomic orbitals. When filling atomic orbitals with electrons, the 1s orbital is filled first, followed by the 2s, then the 2p, 3s, 3p, 4s, 3d, 4p and so on. When we use the diagonal rule to write electron configurations, we use arrows to maintain this increasing order of energy. When we use the periodic table to write electron configurations, we follow the same order of increase in energy of sub-energy levels from left to right. For boron, the electron configuration is 1s2, 2s2, 2p1. The first two electrons fill the 1s orbital, the next two fill the 2s orbital, and the fifth electron occupies one of the three 2p orbitals which has a dumbbell shape. In a main energy level, there are three p orbitals commonly designated as px, py and pz, which are distinguished by their orientation along the x, y and z axes respectively. A p orbital can hold a maximum of 2 electrons and there are 3 p orbitals leading to a total capacity of 6 electrons for the p sub-energy level. That is why the p block of the periodic table spans 6 groups from group 13 to group 18. Boron is a p block element because its outermost electron occupies a p orbital. For carbon, the electron configuration is 1s2, 2s2, 2p2. The first two electrons fill the 1s orbital, the next two fill the 2s orbital, and the fifth and sixth electrons occupy 2px orbital and 2py orbital respectively. According to the Hund's rule, electrons are individually occupy each p orbital before pairing up in the same p orbital to minimize electron-electron repulsion. Therefore, we should not add both fifth and sixth electrons to the 2px orbital because it gives the atom high energy which is unstable. For nitrogen, the electron configuration is 1s2, 2s2, 2p3. The first two electrons fill the 1s orbital, the next two fill the 2s orbital, and the fifth, sixth, and seventh electrons occupy 2px, 2py, and 2pz orbitals respectively. Half-filled sub-energy levels are stable. That is why the first ionization energy, the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of nitrogen is higher than that of oxygen. Oxygen with 8 electrons has the electron configuration 1s2, 2s2, 2p4. The 1s and 2s orbitals are filled with 2 electrons each. The remaining 4 electrons occupy the 2p orbitals. Following the Hund's rule, these electrons fill the 2px, 2py, 2pz orbitals individually before pairing up. For fluorine, the electron configuration is 1s2, 2s2, 2p5. For neon, the electron configuration is 1s2, 2s2, 2p6. Neon has fully filled 2p orbitals and it is a very stable electron configuration. That is why noble gases in group 18 consistently exhibit the highest first ionization energies within their respective periods on the periodic table. Let's see some of the questions may come for the exams from this section. To identify an element, we need to count the superscripts in an electron configuration to find the number of electrons in that atom. If we count the superscripts in question 1, 2 plus 2 plus 2 equals 6. Therefore, element should be carbon. The question number 2 has a noble gas electron configuration. Therefore, first we need to find the number of electrons in that noble gas. In this case, it is helium and it has 2 electrons. Then count the number of electrons. 2 plus 2 plus 5 equals 9. Therefore, the element should be fluorine. For main group elements, also known as representative elements, the group number directly corresponds to the number of valence electrons. To find the number of valence electrons for a main group element, we can sum the superscripts associated with the highest energy level in its electron configuration. An element with the electron configuration 1s2, 2s2, 2p5 has 7 valence electrons and it is in group 17 of the periodic table. Group 17 elements are known as halogens. The period number on the periodic table corresponds to the highest energy level occupied by electrons in an electron configuration. The highest main energy level of 1s2, 2s2, 2p5 electron configuration is 2. Therefore, the period number is 2. When we look at the electron configuration of 1s2, it suggests that it is helium and it has 2 valence electrons. Therefore, its group number should be 2. However, its placement in the periodic table is group 18. This is an exception. It is due to its chemical behavior, not because of its number of valence electrons. Helium is chemically inert, like other noble gases, because its outermost and only energy level is filled with 2 electrons. This fully filled energy level of helium makes it stable and unreactive, aligning it with the properties of group 18 elements. Therefore, when we see an electron configuration of 1s2, we should know its group number is 18 and period number is 1. We already know how to find the group number of an element. Knowing the group number of an element on the periodic table is helpful in determining if it belongs to the S block or P block. S block elements are found in groups 1 and 2, while P block elements are in group 13 through 18, excluding helium, which belongs to S block because its valence electrons are occupied in an S orbital. When we follow the Aufbau principle, we write the electron arrangement with lowest energy configuration possible, and it is called ground state electron configuration. If an electron configuration violates the Aufbau principle, that means electrons occupy higher energy levels before lower ones, it signifies that the atom is in high energy state and it is called excited state electron configuration. That is what happens when we do the flame test. When a salt of an element is heated in a flame, the heat provides energy to the electrons in the atoms of the substance. The electrons absorb the energy and jump to a higher energy level, entering the excited state. However, this excited state is unstable and the electrons quickly fall back to their original lower energy levels, that is ground state, releasing the absorbed energy as light. This emitted light is what we observe as the characteristic color in a flame test.